Welcome everybody. My name is Frits Hoogland. I'm from the Netherlands, so that's probably the reason why I speak a bit funny English. If you want to see more on the stuff I've done researching the Oracle database, you can find it on my blog. I'm on Twitter. If you have questions, you can email me. There's an email address on the slides. I think the slides will be made available after Oak World, and otherwise you can find the slides on my blog. I'm an ACE director and I'm a proud member of the Oak Table. This session today is about microscopic in-depth investigation which I did for the log writer and database writer processes in the Oracle database. This session is a good fit if you have understanding, or at least a bit of understanding, about how a C program works and how a C program calls functions within functions and that kind of stuff. Otherwise, this session probably might be a bit confusing. It also helps if you have some understanding about Oracle and trace methods within Oracle and about how processes interact within the Oracle database. Things change and can change quite rapidly or remain the same for a long time. Oracle doesn't expose how it's changing its internal stuff. Sometimes it's documented in the concepts guide. Most of the time it is totally non-documented. So it's quite important to point out that I've been using a virtual machine. I don't think the virtualization has any influence on what I've done for researching, but still it's a virtual machine running Oracle Linux with a recent kernel, a 3.8.13 kernel, and I've used 11.204 without any patches applied, and I've used ASM with external redundancy. And the database is also 11.204. There is a tiny bit of Oracle version 12.102 in it, but that's at the end. The log writer. The log writer process, as the concepts guide says, manages the redo log buffer. Probably most of the people know that Oracle introduced private strands in version 10 of the Oracle database. So if you are generating redo, it will first be in your own private strand, and eventually it will make it to the public redo log buffer, and then it gets written. I'm quite sure this isn't in the redo log. This isn't in a concepts guide, but it's nevertheless important to realize that. And the function of the log writer is to write all the redo entries from the public general log buffer, and it does so on a user commit, a log switch, and every 3 seconds the process wakes up and it writes anything that is in the public log buffer. So if it's in your private strand, it will not be written. It will also write if it's 1/3 full, or if it's beyond 1 megabyte of contents in the log buffer. And a very interesting one is if the database writer needs to write, then it will first look if all the transactions which are in the dirty buffers have already been written from the perspective of the redo. If not, the database writer will post the log writer and will first write all the redo contents of the buffers before the database writer starts writing dirty logs. So this means that if your log writer gets very slow for whatever reason, it can eventually block the database writer from doing its work. Well, this is an in-depth session, and one of the things I do is use SQL Trace. Tanel in his earlier session showed you the bright new and shiny way of enabling SQL Trace, the brand new way in version 10, that is, by the way. I'm using the very old one using ORDebug, mainly because it's convenient to me. This is how I mostly do it, and I'm using the unlimit clause, so if there is a max dump file size set, it will be reset and it will just write everything. And this way, I'm just enabling SQL Trace. If you put a SQL Trace on the log writer, This is what you typically will see on an idle database. It's the wait event RDBMS IPC message, and it will show an elapsed time of around 3 seconds. RDBMS IPC message is truly an idle wait. As you can see, what it does, what it really times, is a C function called sem_timed_op, and sem_timed_op means semaphore timed operation, and it means it is a way for Oracle as a C program to truly put a process, keep a process from running on a CPU. So this is actually mandatory, so it's not constantly running and looking for stuff. Sem-timed operation means that that a process is truly idle for 3 seconds and doesn't take any CPU slices. And what it does, it issues some other function calls. Also, what it does is every 20th time it looks in proc for a process, and I looked up the process and it's pmon. So if you kill pmon, what you will see, it is a test, it's nice to do on a test database. If you kill pmon, sometimes your database immediately crashes, and sometimes it takes a little time, and this is one of the reasons why. You kill the process, and eventually logwriter will wake up and will see that the pmon process is gone, and as a result it will terminate the database. So, hopefully for most of you this is not really new. In an idle database, the logwriter just sleeps for 3 seconds at a time, will wake up, will see that there's nothing to do, and will go to sleep again, and every 20 time, so every minute, it will look for pmon. But what happens if we insert a row of data and commit it? Well, when I started this investigation, what I thought would happen is, and the upper line is my foreground process, the lower line is the logwriter. What I thought would happen is the logwriter is sleeping on the semaphore timed operation. I issue a commit, and when issuing a commit, what you actually do is execute a C function, and a system call called semctl, and semctl will message the logwriter, and I thought that my foreground process would go to sleep on the semaphore timed operation, because as long as the logwriter is busy doing stuff, it has no business to do anything else. So it will message it. The logwriter will issue an IO submit to introduce a write IO to the operating system, and it will look for the IO to get written, and if it's done, IO get events will detect that the IO is done, and it will issue a semaphore, a semctl back, and it starts waiting on sem_timed_op, and my process is ready. That's what I thought. This works. Looks quite reasonable to me. What I actually found during my tests, and the during my tests part is important here, is it's doing its semaphore timed operation. I issue the commit. Commit means I issue the system call to signal the logwriter. The logwriter, of course, issued an IO submit for submitting the write IO, and found the IO to be ready, and it started sleeping on the semaphore timed operation. What I did miss, I saw no semctl, and I was quite astounded. Also, I saw no semaphore timed operation here, and as a result, I saw no log file sync, and I was quite surprised by it when I did my investigation. What I saw is my foreground process comes into a C function which is called kcrf, probably kernel control redo file, commit force, and inside this function it calls a function called kcscur3, and it will issue it 3 times. And if the data in the log buffer is written within the time that 3 kcscur3 functions are executed, then it will not show any weight. So I was quite surprised by that. And then I turned off all my GDB stuff, which slowed all the processes down, and I did it again. And it turned out that in any other normal situation, which I tried to do, I always see a wait event, because then the log writer is, then my foreground process is speedy enough to issue these C functions, and it will not see. Sorry, it will see the contents to have been written. So this is an edge. It turned out to be an edge case. What actually happens, and what I found out is, it's my process. I issue the commit. The commit issues a SEMCTL. The SEMCTL will wake up the log writer, and the log writer writes. And above you see the KCRF commit force function, and then it issues the KCS curve 3 function 3 times. And this arrow means if this arrow finds that the data is already being written, there will be no wait, because the gray area above indicates what is timed by a wait event. So if the first KCS curve 3 function finds the data already being written, it will not issue a wait event, and it will continue immediately. However, if my IO get events call takes a longer time, and it waits for the IO to be finished because the IO subsystem is processing it, it will start to wait, and it will issue KCS curve 3 times, and it then will go into a SEM timed operation for 100 milliseconds, wake up, checks KCS curve 3 2 times, and do that over and over until it's ready. And because it is on a semaphore timed operation, then the log writer needs to post the process back saying, okay, the log write's done, here you go. So that's how it works in a situation where you got a mechanism called post-wait. And then somebody, Martin Bach, said, have you heard about this new adaptive log file sync thing? How many people know about adaptive log file sync? This turns out to be a completely new mode of the log writer, which is introduced in Oracle 11. Only it was set to false, and starting from version 11 to 03, this feature is set to true. And true means that you start off with the log writer being in the post-wait mode, but when Oracle thinks it's feasible, it will switch to a polling mode, and a polling mode is a new mode of the log writer. It isn't documented in the Oracle documentation at all, as far as I know. And another thing is, Oracle actually does notify you that it switches from post-wait to polling. Only it does so in the trace file of the log writer. And I don't know about you, but I'm not checking all the individual trace files of all the foreground and background processes. I can't do that for all my databases. So this probably goes unnoticed for most of the databases. What happens with polling is Oracle does it a bit different. If you do the commit, the log writer still is sleeping on RDBMS IPC message, which means semaphore timed operation. You issue the commit will still signal the log writer that it needs to write something. The log writer will still write the information in the log buffer, but the process now is doing the same functions first, KCRF commit force and KCS curve 3, but it then will go into another wait and do another system call, which is called nanosleep, and it will sleep for a variable amount of time. And my guess is there is some kind of statistics area in the shared pool where the foreground process tries to determine the amount of IOs and the overall busyness of the database, and then sets a variable number. And actually, when I did my tests, I suspended foreground to background processes for long times, and long, I mean 40 minutes or something. And I eventually saw that my log writer was waiting for, my foreground process was waiting in nanosleep for over a minute before it started checking again. So this probably can't ever happen on a real production system, but even if it's 10 seconds, that is a huge amount of time, and 10 seconds is something which can happen in your database. So there is no log file sync wait event for your foreground if you do commit, if the log writer was able to flush the contents of the log buffer before it submits the first KCS curve 3 function. And if the log writer wasn't able to do so, your foreground session will start a wait called log file sync. And if it is, if the log writer is in the post wait, if the foreground session is in a post wait mode, then it will record that it's waiting in something which is called a post wait queue. And I've searched in the Oracle database for something called a post wait queue quite a lengthy time, and I can find in some Xdollar tables which start with KSL that there is an entity called post wait queue, but I don't think it's externalized anywhere as far as I know. And it will record that it's waiting in a post wait queue and then start sleeping on a semaphore timed operation for 100 milliseconds. And it just waits until the log writer posts back saying, okay, I've written, you're good to go. If it's in polling mode, it's different. Your session will wait in the nanosleep, a nanosleep system call, and for a computer time, which is total variable, and it will just check the progress of the log writer itself. So the log writer doesn't post back that the log writer is ready. And I can see why this can be beneficial. If you have huge amounts of processes waiting, then I think the log writer can spend a significant amount of time in SAM-CTLing all the processes which have committed. And this way, the log writer doesn't have to do anything but write, and the processes all check the progress themselves. So, to recap a bit, the log writer, the main task of the log writer is to write the contents of the reader log buffer. And if it's idle, you will see the wait RDBMS IPC message. If it's busy, I don't think it's exact science to tell if the process as log writer, the process log writer, if it's truly busy. Indicators of busyness are CPU time and the wait event log file parallel write. Another very important thing, if you especially with consolidation, which seems to happen everywhere nowadays, the log writer is a Unix Linux process, and the only way that it can write or do anything is that it needs to get onto the CPU. So if you have a load and the load of your system is way beyond the number of cores, there will be a queuing time in the scheduler of the operating system before the log writer even can get on the CPU, and it can only do stuff like writing and signaling processes that it's ready if it gets onto the CPU. And this boils down to, for example, Kevin Clausen saying, in the end, everything is a CPU problem. So, if you look at the log writer, and the log writer is just being idle, so it's waiting for RDBMS IPC message, and then it gets signaled by a process that it needs to do something. If you look closely, you will see that it does some latch gets. In idle mode, it will take these latches, and if it needs to write there is one additional ledge which is the redo writing ledge. If a foreground process is busy writing its contents into the public log buffer, which the log writer uses to write onto disk, then you will see if a process is busy doing that, it also takes the redo writing ledge because it's writing in the log buffer. And sometimes you can see the log writer waiting for a wait event called log writer wait for redo copy. And that's what it is. Then a session, a process is writing its private strand information into the public log buffer, and it can only write if all the other sessions are not doing something to the log buffer. After it took this it took this ledge, then the log writer can actually start writing. You will see an IO submit. Then the wait event log file parallel write starts, and it will first do an IO get events call with a timeout set to 0. And if this IO call cannot reap the IOs which were submitted with IO submit, it will then start a blocking IO get events call. And the fun thing is, if you use strace, strace, you will either only see IO get events with the last field 0,0, or you will see the field 600,0, which is the blocking call, because the first one isn't shown by strace if it isn't able to reap all the IOs which were submitted. The wait event log file parallel write is an indicator of the IO wait time for the log writer. It is not the absolute IO latency time. So let me show you why. With IO submit, let's say that I need to submit 2 IOs. Both IOs have a certain latency. And if my first IO get events call, which is non-blocking, is not able to read them, then the second one needs to wait for both IOs to be completed. And let's say that is first real IO, the IO time of the first IO is 10 milliseconds, and the second one is 7 milliseconds. Then log file parallel write will say something like 9.85 milliseconds. It is close, but it's very important to realize that multiple IOs can have multiple latency times, and that the wait event log file parallel write is not the exact precise IO latency time. Actually, fast IOs can be completely hidden if you do a lot of distinct IOs with this call. So, our BMS IPC message is a true idle wait, and it has a timeout of 300 if you look at the SQL trace, which is in the old Oracle centiseconds way of saying it, which is 3 seconds. It means that the log writer process is sleeping for approximately 3 seconds. Log file parallel write, if you look at files, files corresponds to the number of log file members, blocks to the number of redo blocks, and the redo blocks are something other than database blocks. Redo blocks are mostly half a kilobyte, but you can look them up. And requests, I don't really know. I've seen this differ from the actual number of IO requests. Now something interesting. Let's switch to synchronous IO, because there are still some platforms which are still quite widely used, like for example HPUX, which do not, well, let's say they have difficulty with IAO, asynchronous IO. They mostly use synchronous IO. And purely by accident, I found out that if you use ASM on top of NFS, so you create files, then if you just leave it alone and you have this asynchronous IO set to true, and you think you're doing asynchronous I/O, and you have file system I/O options set to none, which is async by default, but you have set it to none, then you will do synchronous I/O. And I only found out this by accident. And the client pointed out to me that the documentation specifies that if you use ASM, then all I/Os are asynchronous by nature. So clearly this isn't true. But overall, the last point is, I think, the most important one on this slide. Check your environment. If you're not doing asynchronous I/O now in 2014, you're just doing it wrong. Get it over with. Make sure you use asynchronous I/O. Let's look at log file parallel write with asynchronous I/O. We first see SAMCTL, and we see SAMCTL that the timeout is set to tvsec3, which means 3 seconds. But if you look at the actual end time of the wait event, it's half a second. So that means that the log writer is posted. 2 P writes. Well, I set up my system to have 2 log file members, so I need to do 2 writes. And that's funny. This is the wait event is called log file parallel write. But if you're doing asynchronous I/O, by the nature how it works, it has to do 2 I/Os. It can't do 2 I/Os in parallel. It needs to do them in a synchronous way. So first issues one, and then issues the other. There is no asynchronous thing, and there is no parallel thing happening here. So if you have high latency times on your I/O, this will inflate them, and the whole parallel, which is in the wait event, isn't happening. And so we are doing 2 writes, and I see KSL BCTX, and KSL BCTX is an internal Oracle C function, and this function is actually the start of the wait event. It means kernel service layer wait begin context. But what is funny here, the wait event times between KSL BCTX, which is the beginning of the wait event, and KSL ECTX, which is the ending. The funny thing here is KSL BCTX starts after the P writes, and it's showing a very, very good I/O time. Well, that can happen. I did the test on my laptop. My laptop has an SSD, and on a VM on your laptop, if you're redoing stuff, the actual I/Os come in the cache, in the file system cache of your system. So it can't be. But what you can do in GDB is add a small shell script once a function is encountered. So what I did is I added a shell sleep 0.1, which is a sleep of 100 milliseconds, every time a P write is encountered. So that means that the P writes, the 2 P writes which I'm doing, should at least take 200 milliseconds. And I was just looking if Oracle, for some reason, was able to magically understand that there was wait time involved. But still the wait time is sub-millisecond. So by doing these tests, I convinced myself that the wait time with synchronous I/O on Oracle 11.204 is off for this wait event. And to be clear, this is only with synchronous I/O. Hopefully all of you on your systems do asynchronous I/O, so you don't have, so you're not bitten by this feature. And it can truly bite you if you have an I/O issue and you try to profile it and try to prove something to your storage team, and your number is totally off. It only happens with synchronous I/O. How about the other ones? Control file sequential read. KSL BCTX is before the P write, and KSL ECTX is after it. So it's timed correctly. Control file parallel write. First the P write, and then KSL BCTX. So this timing is off. You can't use this timing to say anything about your I/O times. Log file single write. KSL BCTX is before the I/O call, so it's good. When doing a log switch, the log writer encounters quite some other calls. OS Thread Startup is actually a game where your process asks Oracle to spawn another process, for example a parallel query slave, and it will wait in some timed operation to be semctl to notify the process you wish to have is started now, control file sequential read, which is a pread64 call, a control file parallel write, IO submit, IO get events, etc. KSV master wait, I every now and then see this wait on systems, and it is actually I've seen this as a semctl to the database writer. I've also seen this as a semctl to the CSSD daemon when you're using Oracle's grid software. And this is with asynchronous I/O enabled. So please mind the pread64, etc. If Oracle needs to do a small I/O, if the Oracle database needs to do a small I/O, and it needs the contents of this I/O to process further, Oracle doesn't bother to set up asynchronous I/O and do an I/O submit and then wait in I/O get events. It will just issue a simple synchronous I/O call. So that's probably the reason why all the notes in Oracle on checking if you truly are using asynchronous I/O are so tremendously difficult in determining all kinds of stuff in proc, etc. There are some calls which keep on being a synchronous call, despite that you have enabled asynchronous I/O. Another funny thing. Has anybody seen this warning? This warning is very helpful because this warning says to you that your I/O time of your log writer, or the I/O timing of the log writer, exceeded 500 milliseconds. So this means that there is something going on the I/O layer, which you probably should look at. The reason why, well, I've seen the hands, I think it's two, that most of the people didn't see this. This, again, is only printed in the trace file of the log writer. And just like me, and the vast majority of you too, they're not looking in all kinds of trace files if there's no need to. But this is actually extremely useful information to get an understanding of potential problems. And by the way, if you want to change it, if you're looking for it, the underbar parameter side channel batch timeout is the one which sets this. Only recently I found out that this same message can be true for real application clusters too. If a write broadcast from the log writer doesn't get a response back within 500 milliseconds, then it will print this same, well, essentially the same message, but now indicating that there's something wrong with the signaling in the log writer trace file too. If you see this one, then you will also see the wait for SCN egg. And so that's quite useful. Disable logging. Anybody played with disable logging? Well, probably you shouldn't, because what this does is it will disable writing redo information when doing transactions. When I talk to people, most of the people heard from it, and a lot of people think all kinds of magic is happening when you set this switch. Actually, there is absolutely no magic happening. When you set this switch, the log writer will, the only thing the log writer doesn't do is write. So all the signaling is happening, all the latching is happening, everything is happening except for really doing the write. So it's no magic path or something whatsoever, it's only not doing the write. And as a result, you will only get a valid database after startup if you do a shutdown normal and truly wait for everything to stop. Anything else will corrupt your database because there is no redo information because the log writer didn't write. Is it useful? Well, in as good as any case, no. Why is it there? I guess for Oracle doing benchmarks and cheating, tiny bit, might be. It's a guess, so I'm not accusing anyone.
It's true.
Yeah. Yep. Somebody in the audience said it's true. Actually, you can do something useful with this. One of the things you can do is, if you suspect that your database is suffering from very slow I/O and you want to test if you buy faster I/O, if that will give any benefit, if you disable this, you can at least get proof that if you have truly zero latency for the log writer, which is probably not true even for very fast storage, but if you have very low or no latency for the log writer, if your whole processing then will speed up. So you can test with it, and it can be useful in that case. Other interesting thing, how would this look like on Exadata? Well, this is how it looks like on Exadata. The log writer still waits for a semaphore timed operation, and the I/O submit part, if you would like to call it on Exadata, is called OSS write, and it's Oracle storage software or server write, and it will signal the write to the cells. And the next step is it will issue a wait, and it will wait. It issues an OSS wait for all the I/Os to finish. I'm pretty sure this is a blocking call, and I'm pretty sure that this timing gives you the time for all your I/Os to be finished. So this is actually correctly timed. Then the database writer. The database writer, the essential function of the database writer is to write blocks in the buffer cache which have been dirtied. And it will do in a number of circumstances, most notably when the process can't find a suitable buffer to put its contents in, and if a checkpoint is happening. And guess what? The database writer more or less follows the same pattern. It sleeps on RDBMS IPC message, and in between it does nothing if it doesn't need to. And also every 20 times, so every 60 seconds, it will look if the payment process is still alive. So that's the same as with the log writer, so that's fairly simple. If we want to force the database writer to write, you can issue an alter system checkpoint, and it will then write. I guess there are more ways. This is the method I used. And this is how it looks like. When you enable SQL trace and you look in the trace of the database writer. We wait on RDBMS IPC message. After RDBMS IPC message, I see a wait, and I was quite surprised to see this wait. This wait is called DB file async IO submit. And to me, it looks like Oracle understands that it can do a huge number of writes via IO submit. So it decided to time the IO submit system call. After DB file async IO submit, we got a DB file parallel write. A DB file parallel write is actually the wait event waiting for the write IOs to finish. Now let's look at the Oracle wait events together with the actual system calls. And this can be done by enable SQL trace. And if you enable SQL trace and you put strace on the process, you can see them both. If you emphasize strace to also look at all the writes, because it then will print out the write information, which is the trace information, and it will show the system calls. And this is how it looks like. And the first one we see is an IO submit, and the IO submit corresponds to the DB file async IO submit wait event, and then we see IO get events, and IO get events corresponds with the DB file parallel write. Now let's look a tiny bit deeper. If you look, we see request 3, and request 3 corresponds with 3 IOs which are submitted onto the operating system. So that means we truly submitted 3 write IOs. And we see also interrupt 0, haven't got a clue what that is, and we see timeout 0. Well, that more or less makes sense because IO submit is supposed to be non-blocking. And then we see requests 1. So, so we've written 3 blocks, and it will only, it says requests 1, so apparently it's only waiting for 1 I/O request. And this corresponds to the number 1 there, and the number 1 there in I/O get events means the minimum number of I/Os it's supposed to be waiting for is 1. Here we see too interrupt 0, again no clue what it is, and a timeout of a big number. And if you look at the timeout value of the I/O get events call, it's 600 seconds. That means that means 600 seconds, a couple of minutes. And the result of my I/O get events call is 3. So it means, despite asking for 1 to finish, this call got all the 3 calls of the I/O submit call I previously did. So I submitted 3 and gotten 3. Interestingly, this information is not externalized. So it means that my I/O get events call can just get 1 I/O whilst I submitted 3. And I never can tell by looking at a wait event, because the wait event says 1. Well, we saw I/O, we saw DB file async I/O submit. Let's look at the documentation. Isn't any? Actually, searching my Oracle support, I found 2 articles mentioning DB file async I/O submit, and both don't describe what a wait event actually is. Interestingly, one of the notes said that this wait event apparently came in with version 11.202. So, what does this wait event mean? It looks, and because the wait event comes in after I/O submit, it strongly looks like the instrumentation of the I/O submit system call. The answer is, I haven't got a clue. But it's definitely not the instrumentation of the I/O submit call. Because if you look at when you trace the information, you see I/O submit first. Well, you see first the beginning and the ending of the semaphore posting by the BMS IPC message. Then I/O submit, and then we see the wait event whilst the wait event timing starts after I/O submit. So it can't be the timing. And then we see the I/O get events call, which is correctly timed. Just to be sure, in case any magic is happening, let's add a sleep of 100 milliseconds on the I/O submit call by breaking on it. No, this is sub-millisecond, and I've waited for 100 milliseconds, so I've added it. I'm quite sure that this wait event maybe means something, but definitely does not mean I/O submit is tracked. Now let's look at the DB file parallel write wait event. This is what the documentation says. This is the documentation of version 11.2. It says this event occurs in a database write. That's correct. It indicates that the database write is performing a parallel write to files and blocks. Correct, if you are using asynchronous I/O. By nature of synchronous I/O, this can't be true because it has to issue the P-writes one after another. And when the last I/O has gone to disk, the wait ends. Well, this is absolutely not true. It just waits for one. And there can be other I/Os in flight.
Yeah, but doesn't that make sense to wait for one? Because otherwise, if you stated 50 I/Os and you had one very slow, you would have to wait to the next write. Because if you're managing your queue of writes, so you get the first, you can actually issue a new write and wait for one, and then you're picking up the last ones. Otherwise, you would wait unevenly long without filling up your I/O queue request queue. So it makes sense from a queuing perspective to wait for the first. Because then you can actually issue a new write.
Yeah, somebody mentioned that it makes sense, and I think essentially what you're saying is you have asynchronous I/O. Why not make use of it?
Yeah.
That's what you, in essence, say.
basically.
I fully agree with that. Of course, on the other hand, knowing that your writes are truly written to disk is also very important because you want all your data to be consistent.
Yes, but since you're only writing blocks, the consistency will be because you will get a post wait for each, basically, when they're all finished in the code, so you eventually will know all the blocks are written in the post wait of asynchronous. So there's no reason for programming point of waiting for it.
The other comment is that it's reasonable because all the IOs are still tracked. I'm trying to summarize what you say. All the IOs are still tracked, so why wait for it? You can just look if eventually all the IOs are truly written to disk. Yeah, I agree with that. But let's continue. Requests. The requests of the DB file parallel write. The documentation says this indicates the total number of IO requests, which will be the same number. As blocks. Truly incorrect. Interrupt for convenience has been non-documented, and the timeout indicates a timeout value in hundredths of a second to wait for the I/O completion. Excuse me, this has 2 billion as a number in it, and if I divide it and look what it means, it's 248 days. Well, it's quite unlikely that I'm going to wait and that it even makes sense to wait 248 days for an I/O to complete. This might be a bit off.
I can take this like that.
So, as a recap of the previous traced call, if you look at I/O submit 3 IOs, I/O get events waits for 1, and 3 are returned, and this is not visible in the wait interface. Okay, but this is in a situation where my IOs are very fast. How about severely limiting my I/O capacity of my system, and look what it does then. What it does then, with the database writer, which is a throttle to do 1 I/O per second, and I've now generated more dirty blocks. I have 366 blocks dirtied, and I issue the alter system checkpoint, and as a result, the database writer issues 366 IOs onto the operating system, and I/O get events. So what a database writer will wait for is 100. I found out, but I think I'll get to it later, that in my idle database, Oracle calculates the number of IOs to wait for the database writer to be somewhere between 25 and 33%. That's typically what I see in my idle database. So it can be hugely different if you have a database which truly does stuff, because mine is just for testing purposes. So it says I'll wait for 1, and guess what? Because it's severely throttled the database writer in doing IOs. It also waited just for 100 IOs to finish. So now I've got a situation that I'm past my wait event. I have 366 IOs submitted. I waited for 100, so 266 are still in flight. Surprisingly, what Oracle does then is it will issue a couple of IO get events calls, non-blocking, after the wait event, just to pick up some more IOs. And it makes sense, but it's non-timed. You can't see it only if you trace system calls, and it will just reap some other ones for the fun of it. And if you have more IOs, let me get it. If you have more IOs, IO submit, the database writer will then introduce new IOs. No, this is 367. So, I started thinking about this because I found this was not what I expected the database writer was doing. So the database writer clearly submits the IOs it needs to write. It waits then for a variable amount of IOs to finish in the wait event DB file parallel write, which seems to be 33 to 25% of the submitted IOs. It then does two non-blocking IO get events called to read some more, and then it either submits again or it goes in DB file parallel write for a subset of the IOs in flight and just circle through until all the IOs are finished, and then goes back to sleeping. So, what is extremely important, and especially for people looking into a database writer performance, DB file parallel write has nothing, absolutely nothing to do with physical IOs, with the number of physical IOs. You can't tell anything about the number of physical IOs because it can read more IOs. It is the minimum number of IOs it can read, but it can be way more. And it has nothing to do with IO latency. And that's an extremely important one, because if you recap what you just saw, if new IO is submitted and it starts waiting again, what the IOs which IO get events will wait for probably are the IOs of the previous IO submit. So it has nothing to do with IO latency time. So my conclusion, and this is still just by looking at the bits and pieces which I have here, is my conclusion is this mechanism is something Oracle created in order to throttle the number of IOs which are submitted onto the operating system. Because if you're doing operations on tables, the number of blocks which get dirty can be huge. And if you, via this mechanism, slowly introduce batches of IOs, it doesn't flood your entire IO subsystem, but it gradually introduces writes to the operating system. Again, this is totally open for debate. Yes, Jonathan?
You said, you gave the example that you were using alter system checkpoint.
Yeah.
Did you also try other ways of getting the database writer to write? Because alter system checkpoint, of course, is something that should finish fairly aggressively, and therefore you might have some very different strategies built in the code if you're not doing the checkpoint.
The question is if I only checked alter system checkpoints, because alter system checkpoint means that the database should quite aggressively write its IOs to disk. Is that a good recap?
Yeah.
My answer is no. I just gone with this because it was so puzzling what I found eventually that I didn't try other mechanisms of forcing the database writer to write. So that's a good question. I've tested this situation, the exact situation which you saw, and this is my conclusion in this situation. Next up, asynchronous I/O. What if you turn it off? Because I'm using ASM, what I did is simply set disk async I/O to false, and that means that the database falls back to mandatory P writes and P reads instead of IO submit and IO get events. I set a SQL trace on the database writer again and did the same. Insert into followed by the commit and then alter system checkpoint. What I saw is I'm doing P writes now, and P writes means synchronous I/O. And I see DB file parallel write for 3 requests. And I see a second DB file parallel write wait event, which probably, well, maybe Oracle wants to emphasize a point, but yep, there is no DB file async IO submit anymore, and that's good because we don't have an IO submit phase because we're doing synchronous IO. We just write and that's it. And the DB file parallel write wait event seems suspicious because it looks like the wait event is issued twice. And further investigation says, yeah, it's probably a bug in the implementation. There shouldn't be a second wait event, but there is. Now let's look a bit deeper. First, The semaphore, the process gets posted via the semaphore. I'm doing the p-writes, and again it says DB file parallel write, but if you're using synchronous I/O, it can only synchronously issue the p-write, so there is no parallel there. And then we see KSL, BCTX, and ECTX after the p-writes. So when you're doing synchronous I/O, your timings are bogus, and after it continues sleeping. Well, let's issue the trick. Well, I've by now done this trick so many times, and I know there isn't any magic, but still, I did it. I added 100 milliseconds, and the timing is very small. It doesn't do any magic. The timing is just time off. So, if you're doing synchronous I/O, your events for the database writer are absolutely not properly timed. And DB file parallel write is issued twice your trace file for no apparent reason to me. How does this look like on Exadata? And this is actually quite interesting. I've introduced a couple of dirty blocks. I/O writes, well, the submission of the I/Os is not captured by any wait event, so it's just issued. It's shown as CPU time essentially. These are the writes. There is an I/O submit, but it doesn't time anything as far as I know. And then interestingly enough, quite consistently during the limited tests I did on Exadata, the wait time for the first two I/Os with Exadata are actually timed, and it needs to wait for the other ones, so it's less asynchronous, but this is non-timed. I think this is because Oracle need to fit this in the current database code, but if you introduce a lot of I/Os for the database writer, only the first two are timed, and the other ones are, well, not to be seen in the wait interface. Quite interesting. So, as a conclusion, the log writer when idle waits on RDBMS IPC message, which is a way of Linux and of Unix to keep a process off the CPU, and it gets posted with SAMCTL, and it only writes when it really needs to do something. And starting from version 11.203, there are two methods for posting the foregrounds from the log writer, which is polling and post wait. Post wait is the default, and it can switch to polling during runtime. If it does, it will tell you in the log writer trace file. So if you see suspicious things, look in that file. And with polling, the foreground process waits for a variable time. And I've seen multiple people saying there can be issues with the polling mechanism. And most of the sites, the problems were resolved by forcing, well, essentially by turning the polling mode off and relying on post wait. If you look at the wait events calls, log for parallel write are I/O get events calls. And this is not true I/O latency. It is an indication of I/O latency and of the slowest ones. So it might hide fast I/Os. And when doing synchronous I/O, it doesn't do any parallel writes. It does them serially, and it doesn't time any I/O then. And the timing, all the parallel read and parallel write wait events do not seem to time I/O correctly with version 11, at least up to 12.101. I come to the 12.102 in a minute. And all the events which cover single block reads are timed correctly. If there is an issue with either writing or communicating with other log writers in REC, it will give a warning in the trace file of the log writer. This is truly something interesting. And disable logging only disables the write to the log files. It doesn't disable anything else. For the database writer, roughly the same. When it's idle, it's sleeping on a semaphore, which means that it does not get onto the CPU, and it gets posted by SAMCTL to do work. And it only writes when it really needs to do something. Since version 11.202, there is DB file async IO submit, and it does not show with synchronous I/O, and it shows the actual amount of I/Os which are submitted, and it does not time I/O submit, whilst the name strongly hints at it. DB file parallel write, it shows the minimum, the number of blocks with the wait event. DB file parallel write shows the minimum number of blocks which it waits for, but it can reap way more I/Os. And the minimum number seems to be something around 25 to 32% of the submitted I/Os. And after the timed blocking I/O wait events call, it will issue 2 other I/O get events calls which are not visible if there are any non-reaped I/Os left. And I think this is some kind of way to spread out I/Os, to not have them all submitted at once. DB file parallel write also is the wait event with synchronous I/O, but it issues them in a serial way, and it does not time at all. And on Exadata, it shows only the timing of the first 2 I/Os which are ready, and all the other ones your foreground, the database writer will wait for, but is not visible. I tried to show my timing findings to Oracle, so I opened my Oracle support. Am I over time?
Yeah, it's time.
Okay, very fast. Log file parallel write with asynchronous I/O. The wait now includes I/O submit. I didn't expect this, but this is log file parallel write. With synchronous I/O, all is now timed well with log file parallel write in version 12.102. And DB file async I/O submit still is lost there. And DB file parallel write is not changed with asynchronous I/O. And with synchronous I/O, the first wait now shows the true waiting time. So, well, I'm over time, so if you have any questions or remarks, then please, I will be over here and ask me then. Thank you.
Thank you.